It's my great pleasure to present our today's speaker, since I'm kind of familiar with his works, and I'm currently reading these works to prepare my PhD thesis. So our today's speaker is Professor Shi Wei Chu from National Taiwan University, and he'll be giving a talk on giant photothermal nonlinearity of plasmonics and silicon nanostructures and applications towards super resolution. So please, the stage is yours.
Okay. Yeah, thanks, George, for kind invitation and the arrangement. So, good morning. Yeah. So my time zone now is 3 p.m. So, but I understand it's 10 a.m. in Russia. So it's not easy to wake up and attend the seminar talk. But I hope I can do my best to providing an not only interesting but also entertaining presentation of the topic about giant nonlinearity of plasmonics and the nanosilicon. So during my chat with George and also Pavel, I understand that many of you are working on nanomaterials. So the topic today is about how to induce very large nonlinear response in metal nanoparticles or in silicon nanoparticles through photothermal interaction. However, my main background is not nanophotonics. My main background is actually on optical microscopy. So I start my career by using optical imaging in biological tissues, looking at like zebrafish, like Drosophila, and now recently I work extensively on brain imaging. So I would like to start from the perspective of imaging and then link this imaging, say super resolution imaging, to giant nonlinearity of nanomaterials. Oops, so how should I change my page? So I'd like to start from this quote from Sidney Brenner, who mentioned that the progress of science depends on new techniques, new discoveries, and new ideas, probably in that order. So if you look back into history, many of the new scientific discovery actually follows new technology development, because new technology development allows you to see something that is previously unseen. So that's why I mainly work on optical microscopy, because it allows us to see either biological tissues or material systems that was not be able to see before. So one part of my research in imaging is mainly on contrast, especially in nonlinear scattering that we are going to cover today. So these are several sample images that we are going to see today. The other half of my study is about imaging in biological tissues, which related to, say, for example, resolution. I developed a super resolution imaging in deep tissue, which can penetrate through the whole Drosophila brain and resolve detailed neuron fibers inside. By the way, can you see my mouse?
Yeah, sure. I see your mouse. Yeah.
Let me make it. Yeah, maybe like this one. So
yeah.
Yes, so I can see this 80 nanometer thick fiber distribution inside a whole intact Drosophila brain. So we published it last year, and we also demonstrate whole brain imaging through multi-photon imaging that's mainly about imaging depths, also in Drosophila brain. And we also develop a very high-speed 2-photon imaging system that allows us to see individual neuron functional response. So these are other works that I was working on. But today we will focus on only the left-hand side, which is nonlinear scattering of nanoparticles, and this is mainly about contrast. So since I'm working in optical microscopy, I would like to start from this question that if you think about optical imaging, I believe many of you have used, I should say all of you have used optical microscope before. So if you consider microscopy, there are several important factors to think about. Say, for example, if you want to purchase a new microscope, these are the factors that you should consider, including, say, contrast, resolution, penetration depth, and imaging speed. So my question is that, may I invite everyone to choose one, only one. Say which one is the most important factor when you consider to purchase a new microscope. So let me turn on the question. So you should be able to log in this website, and you should see a question in this website. And please try to answer that.
Yeah, just in case I drop the link in the chat. So if your QR code scanner is not working, you can follow the link in the chat. So yeah, sorry, thank you.
Right. You can use the QR code to join the online multi-choice question. So let me see. Good, the answer is coming in. But not many, only 4. And good, so let's try. So let's wait for 1 minute, and please make your choice online. And by the way, if you are not sure about the definition of these specific terms, please feel free to ask questions. So you are welcome to interrupt my talk anytime.
So resolution means spatial resolution.
Yeah, spatial resolution.
Okay.
Temporal resolution is in this imaging speed.
Okay.
Yeah, so this is spatial resolution. Yes.
And penetration depth in terms of some biological tissues?
Yes.
Okay.
Yeah, for example, if you want to look at your finger, can you see muscle tissues and the blood vessels inside your fingers?
So that's why you have to use some near infrared, so something like that.
Yeah. Typically, you use near infrared to penetrate deeper. Good. Yeah. Even though it's not everyone, but we have 10 people here. How many people do we have? 15. So yeah, maybe not finished yet, but at least from this result, we can see that more people choose resolution, and yeah, less people choose contrast, and nobody like imaging depth, nobody like imaging speed. Okay, I understand why, but yeah, so that's what I want to emphasize first today, because typically, I mean, when I give this kind of question, I have been given this question like more than 100 times in talks. So very often, most people choose resolution. However, I would like to make a point that if you have no contrast, no matter how good is your resolution, you see nothing, right? So if you ask me, what I'm going to choose is contrast. And the reason is because, once again, no matter how good is your resolution, you need to see things first. And contrast means what you can see in an image. So George talked with me a few minutes ago. You can also define contrast as signal to noise ratio. So you can think about this. If your signal to noise ratio is below 1, say much below 1, no matter how good is your resolution, you see nothing. Okay, that's why I would like to emphasize here, if you think about imaging, you should think about contrast first as your most important consideration. When you have very good contrast, then think about resolution. So to make this point stronger, I would like to review the development of optical microscopy in the past century. So if you look back 20th century, most of the important development in optical microscopy are contrast. For example, this is dark field microscopy that many of you used to look at nanostructures. Dark field provide very good contrast on the sample, especially on the scattering sample that you want to see. And these are phase contrast, which receive Nobel Prize in physics. And this is differential interference contrast. And in biology, most people use fluorescence as a contrast because fluorescent molecule can label specific target that you want to look at. And only this labeled target has color, like you see here, blue is the cell nucleus and the green is the cell fibers. Only this labeled part has color. Everything else is dark. So it provides very high contrast and very high specificity on the structure you want to look at. So this is the contrast enhancement in the past century. And the major development of optical microscopy in this century, say in recent 20 years, is about resolution enhancement, because we already have very good contrast, for example, fluorescence contrast. So based on fluorescence contrast, now what we can do is to enhance image resolution from the left-hand side to the right-hand side. So the resolution can be enhanced by about 1 order of magnitude. So all the fibers inside, all the small structure inside, you can see very clearly. And the technique that enables this super resolution imaging has been awarded the Nobel Prize in Chemistry 2014. And the reason they were awarded in chemistry, not in physics, is because they are playing with molecular dynamics. So not really break diffraction limit, but play with the molecules so that it allows you to see something that was unseen before. So this is what happened during the past 20 years, super resolution imaging. So I would like to spend about 3 minutes to introduce you what happened to allow them to break this resolution limit. And there are two major points. One is about saturation. If you can achieve saturation of your signal, you can get super resolution. The other possibility is to switch on off your signal, then you can do super resolution. So there are various technologies in this field, but due to time limitation, I only introduced two important things to you. So one is about saturation. So let us think about how saturation can lead to resolution enhancement. So this is a focus intensity distribution in X and the Z plane. So as you can see here, the intensity should be stronger in the center and weak in the peripheral, in the edge part. So if you think in this way, if the signal saturated, where does the saturation start, right? You should be able to understand that the saturation must start from high intensity region, which is in the center. So you can manage the system that the center already saturated, but the edge, the peripheral, is still not saturated. So if it's the case, then the next question is, if you can find a way to separate saturated region from unsaturated region, then you can effectively enhance resolution because you only look at saturated region. So how should we separate saturation region from unsaturated region? There was a straightforward method to do this, that is to introduce modulation into your excitation. So when everything's linear in this unsaturated area, everything's linear, so the emission, say the fluorescence emission, follow the incident excitation modulation perfectly. So when you make a Fourier transform, you only see one frequency, right? However, in the saturated area, because the signal deviates from perfect sinusoidal modulation, then if you make a Fourier transform, you start to see multiple high order frequency components. That is, when you perform an image, when you have a modulation in your excitation, if you look at the second harmonic, third harmonic of the incident modulation, then effectively you can saturate it. You can separate saturation area from unsaturated area. So this was demonstrated in 2007. They used this so-called saturated excitation microscopy, SAX, to improve resolution. So this is linear, say 1F image, and this is a nonlinear, say 2F or 3F image. You can see immediately clear resolution enhancement. The other technique that I want to introduce you is to enhance resolution by switching the fluorescence on and off. So if you can switch the fluorescence on and off, the trick that was invented by Stefan Hale in Germany is that you can switch off fluorescence by stimulated emission. Sorry that I won't go into too much detail here. If you are interested in this, please visit Nobel Prize website in 2014. So, but the main idea here is that if you can switch off fluorescence by, say, the red beam, green light is the fluorescence, and if you can switch off this fluorescence by a red beam via stimulated emission, and you form this red beam into a donut shape, then you increase the intensity of the donut shape. Like I can increase the intensity of the donut shape, so the green fluorescence will be suppressed more and more and more. In the last, only a very small center spot are allowed to emit green fluorescence. So the effective resolution is enhanced via this suppression of fluorescence by stimulated emission. This is called STED technology. So you can compare this confocal imaging and a STED imaging of neuron fibers, and you can see immediately that STED provide much better spatial resolution. So this is another technology of enhancing resolution. So we can rely on saturation or switch on off trick to enhance resolution. So this previous technologies all enhance spatial resolution via fluorescence. So they manipulate fluorescence molecules so that the price they receive is chemistry, not physics. And today, what I like to introduce you is about what we are doing now is to introduce a new contrast. As I mentioned earlier, contrast is the most important thing you need to consider when you do imaging. So what we are doing now here is to introduce a new contrast on scattering, so not fluorescence. And first part covers the plasmonic scattering. So we know that we need, say, saturation of scattering or switchable scattering to enable super resolution. So I will cover 3 parts here, which is that saturated scattering, switchable scattering, or reversible saturated scattering. So I will cover them one by one. And the first we start from saturated scattering. So I believe everyone here knows this surface plasma resonance, so I won't talk too much here. What we use here mainly is 80 nanometer diameter gold nanoparticle. So there is a resonance around 550 nanometer, and this is well known in, say, glass in church. They are consist of very small metal nanoparticles that give this bright color. So one question for everyone here. I guess every one of you have seen this scattering from nanoparticles. I mean, even not in lab, maybe you see that in church glasses. So I want to ask you, does this plasmonic scattering saturated under strong light illumination? So there are 4 options. The first one is yes, the second one is no, third one is depends, and the fourth is I don't know. So once again, please choose your answer online. So let's wait for 1 minute. So if you just joined, please use this link or this QR code to join this online questionnaire. And now I want to know your opinion on, in your intuition, does scattering saturate? Okay, we have 6 here.
Yeah, just a quick reminder, the link is in the chat. If someone has joined the seminar recently, you can use the link in the chat. Yep, thank you.
Yes. I'm not sure how to move this. Ah, okay. So this won't block.
I wonder if option 4 is the correct answer.
Well, just be honest. I mean, if you have no idea, you can say no idea.
Okay.
But that's certainly one of the purpose today, to share with you how can we achieve this. So, wow, that's nice. I really like this kind of distribution, because that means within our audience, the answer is really diverse. And typically if this is a class, then I would invite people to discuss with each other. But somehow I don't know, I have no idea how to do this online. So I'm sorry for that. But I hope this is give you a very good feeling that scattering saturation is really a non-intuitive concept. So let me see. 4 of you choose yes, and 3 say no, 3 say depends, maybe saturated in some case. So may I invite anyone who choose 3 to speak? What is the case you think about? Anyone who choose 3 want to say something? Can I do this, George? Can I invite someone to talk?
I chose first somehow, but let's. I also encourage people to. Okay,
yeah.
I also chose 1, yeah. So I'm not convinced.
Yeah, that's good. But I really want to invite someone who choose 3. Anyone choose 3? Because I'm wondering what kind of case, what kind of situation you think scattering can.
I think number 3 includes number 1, or number 1 includes number 3. So I think answer
but number one means more definite. It says
okay.
yes, of course,
okay.
scattering can iterate, right? But number 3 say sometimes can, sometimes cannot.
Yeah, so, I would say it might depend on the side of the resonance you are pumping, on the left or right of the resonant frequency.
Yes,
then it might saturate or not saturate. That's what I expect, at least.
Okay, good.
That might be.
Yeah, you are the expert on this. So yeah, we are going to see this. If we pump on different side of resonance, we are going to see different response on the spectrum of nanoparticle. Yeah,
so there's a message in the chat by Dr. Sergey Makarov. He is mentioning that it depends on the temperature. So one should, I think, consider this as well. So the temperature of the resonator.
Okay, good. It depends on temperature. I guess that's also because Yonatan Sivan, who gave a talk a few weeks ago, also mentioned this, right? Thermal plasmonics. So very good. Yeah. So let me continue to tell you our recent result on this nonlinear plasmonic scattering. So I would say certainly scattering of plasmonic particles can be saturated. And interestingly, even if you excite on, say, the left-hand side or right-hand side of the resonance, they all saturate. But for silicon, it is not the case. So we are going to see that. So this is our result a few years ago. I should turn this off, sorry. This is our result a few years ago in Physical Review Letters to show the first saturable scattering in plasmonic nanoparticles. Sorry, I don't know how to make it smaller so that because it blocks part of my screen.
So I think we see all the plot itself.
Oh, really? So even when I spread everyone's face out, then you still see the whole screen?
Well, at least myself, yeah, I see the screen. Maybe
yeah,
something else.
I think we see.
Okay.
Yeah, thank you.
Okay, good. Yeah. So so here we are using here we are using 18 nanometer particle, and we use 3 different wavelengths. So one is purple wavelength 405. This is outside the resonance, and one is blue 532, which is on the left-hand side of the resonance, and one of the red, which is on the right-hand side of the resonance. So you see both of them see saturation phenomena. And for the green part, the green laser, the threshold is lower because this is closer to the peak of the plasma resonance. So the threshold of saturation is lower. And because the purple one does not see any saturation effect, so we can immediately understand that this saturation effect must be due to this plasma resonance. And
I'm very sorry, Professor. So there's a quick question in the chat by Dr. Alexey Shcherbakov. So could you please give comments on how it was measured?
Oh, yes. I didn't put the setup here. So what we are using here is basically a reflection confocal microscope. And the laser here are all CW lasers. Is that good enough?
Well, at least for me, yeah, thank you very much. I think it's more or less a standard technique.
Yeah, it's a standard technique. The technique here is not really specialized technologies. Okay. Yep. So the title of this talk is about giant nonlinearity. Why we call this giant nonlinearity is because if you convert this response to N2, which is typically used to describe nonlinear property of a material, so the equation is like this. So this N2 is related to the excitation intensity you need to modify the original index. So you can immediately see from this figure that because the response become nonlinear around 10 to the 4 to 10 to the 5 watt per centimeter square. So the value of N2 is about the inverse of the intensity. So the N2 is about 10 to the minus 5 centimeter square per watt. And I convert the unit a little bit to be micrometer square milliwatt, and this is about 1. So this N2 here on a single metal nanoparticle is 1 micrometer square per milliwatt. This value may not look large. However, if you compare to all the reported nonlinear index of gold, so no matter it's bulk or nanoparticle, then all the value reported today, this is a different mechanism like intraband, interband. This is fast, and this hot electron, hot lattice is slower response, which is related to thermal response. And so all the reported nonlinear index now is much smaller than what we see in this plasmonic nanoparticle. So I hope this gives you a flavor why this is called giant nonlinearity, because due to the Mie-resonance of this nanoparticle, it really enhances the absorption of light very efficiently, and the heating also change the Mie-resonance. So the mechanism.
I'm very sorry. So there was like another question regarding the previous slide. So Dr. Sergey Makarov is asking, 10 to the power of 7 watts per centimeter squared should correspond to strong overheating of nanoparticles. Did the authors consider temperature calculations? Maybe sorry, even previous slide. Maybe even previous slide.
Not even, sorry, this one.
Yeah. So
yes.
So the power, the excitation intensity over here is 10 to the power 5 or 4.
Yes.
So yeah, I think
the even previous one, 10 to the 7. This one.
Yeah, maybe in here. Yeah. So I wonder if the authors consider the optical heating calculation, since 10 to the power 7 is pretty intense laser.
This is pretty intense. So the whole mechanism is basically thermal effect. So this 10 to the 7 is really high, but this is outside the plasmon resonance band. So the percentage of the energy that is absorbed by a nanoparticle is much less than 532 and 600, and this red, 671 nanometer laser. And the reason that everything here is linear is simply because this is not in the resonance. So when we pump even very strongly with 405 nanometer laser, there's no shift, no change of the resonance. This 405 this 405 nanometer is not in the band. So even if the resonance change, this 405 nanometer does not see it. Do I answer clearly?
Sure. Also, Sergey, are there any comments on that? So while maybe Sergey is typing, so there's another comment by Yonatan Sivan. So he wonders, he doubts about the values associated with the hot electrons you've put on the next couple of slides.
Well, this is a value simply from Boyd reference. So this paper actually summarizes the third order nonlinear responsibility of gold. So we just use this paper as a reference to compare the nonlinear index of gold nanoparticle versus other mechanism.
Sure, Boyd's paper is a review, he quotes others. It's not his own work. I'm saying that Boyd's paper is a review, it's not his work, he's quoting others.
Certainly, this is a review. So I put it here, that's why I put the whole reference out, because this is just a review paper that I get this information. Do I answer
the reason for my doubt is that because our theory showed that hot electrons are orders of magnitude smaller than the effect, or the amount of energy going to them is 8, 10 orders of magnitude less than thermal. So I can't imagine a situation where the nonlinearity associated with them is so much higher. But this wasn't studied carefully, at least from the theoretical point of view.
Okay, yeah, well, you are the expert on theory, so certainly this study would be very interesting. Yeah, but for me, currently what I show is numbers cited from that paper. That's why I put this paper down here. Okay, so should I continue?
Well, yes, please. There are no more questions currently.
Okay, so yeah, thank you for your active response. I really enjoy this kind of interaction online. Yeah, and so the mechanism of nonlinear scattering is I think we already mentioned that it's about thermal. So we heat up the particle, and if you look at the scattering cross section, this is a simple Mie scattering equation for spherical nanoparticle. So the most important parameter here is because at the resonance, this real part cancel each other. So what really matters here is the imaginary part of the particle permittivity. And so we can see that scattering cross section is inversely proportional to this imaginary part. So if we increase the damping term, the imaginary part increase and the cross section is reduced. That's why we can see saturation of scattering. So what can cause damping term to increase? And we know now it's about temperature. So we did a control experiment by heating up the nanoparticle. So the left-hand side is to measure the whole spectrum, whole scattering spectrum with light, with excitation at 561 here, with increasing intensity. So you can see the whole spectrum drops as the intensity of 561 increase. And the right-hand side is we increase temperature of the nanoparticle. So you can also see that the scattering spectrum drops quickly. So this is due to the photothermal effect of reducing scattering. That's why we see this nonlinear response. And for detailed description, yeah, Yonatan's here. So I would like to guide you to this excellent paper that he writes. And I believe he has some more papers coming out recently about the mechanism of this nonlinear scattering. So I won't speak too much detail here, but he explained very nicely how to address this reduction of scattering cross-section at high intensity CW laser excitation. And we found that as an experimentalist, we found that this kind of nonlinear scattering is really ubiquitous, which means you can see everywhere. For example, we can see this from in silver nanosphere. And interestingly, we see saturation and also reverse saturation, which means when you have higher enough intensity, the scattering intensity actually increase after certain excitation intensity. And we also see that in golden nanorod, we published a few years ago, saturation and reverse saturation. Something we didn't publish yet is that we also see this in bow tie antenna. So you can see nice saturation curve in this bow tie antenna. So we can see this nonlinear scattering everywhere in plasmonic nanostructures. So as mentioned earlier, my main field is actually optical microscopy. So what I want to do is to use this nonlinear scattering as a new contrast for super resolution. So we mentioned this SEX imaging a few minutes ago. So now we know that we have saturable scattering in plasmonic nanoparticles. So if we combine these two, saturated scattering plus SEX, then what we see is here. So this is an SEN image of several particles, and this is 1F imaging of two particles that are close to each other that you cannot distinguish. And for 2F and 3F, which is a nonlinear term of the modulation, and with this nonlinear modulation extraction, then you can see nice resolving two particles here. So by looking at the full width Hertz maximum of this 2F and 3F, we know that we can enhance resolution down to λ/8. And we published this in 2014, which is highlighted by American Physical Society. And we can use this as a label-free imaging, super resolution imaging contrast to look at hotspots in metallic nanostructure. For example, this is one strange metal nanostructure that we're seeing in our sample. I think this is an artifact due to sample fabrication. However, you can see that in this strange structure, there are several hotspots due to this plasmon resonance. So this is 1F imaging with lowest resolution, and this is 3F imaging. With that, you can clearly see the location of individual hotspots. That's what I say, label-free super resolution imaging. So this is one potential application of this nonlinear scattering. And we can also use this plasmonic SEX in biological tissues. So because this plasmonic modulation can, this nonlinearity keeps no matter how deep it is in the tissue. So one typical major difficulty for super resolution images is that if you go into tissues, the super resolving capability reduce or diminish. So we demonstrate this that we can achieve constantly threefold resolution enhancement throughout 200 micrometer in depth in a biological tissue. So this 3F imaging always have threefold resolution enhancement over this 1F image, no matter how deep is the tissue. And the reason it is 200 microns is simply because this is the working distance of our objective. So this is also published a few years ago. So this is the first part of our contrast plasmonic scattering about saturated scattering. And the second point is switchable scattering. So now we already have saturation. And you can imagine that when we pump one particle into saturation, at this moment, if we add another light onto the same particle, this new coming light actually does not scatter because the scattering cross-section is already saturated. So this new coming light does not see the nanoparticle, which means we can use the original light to pump the particle into saturation and turn off the scattering of another beam. This is the idea of switchable scattering. And this is demonstrated here. So now we overlap two laser beams together. One is an orange beam at 592 nanometer. One is a green beam at 543 nanometer. And at the low intensity, right here at the low intensity, we observe this vertical axis is the green beam scattering, and the horizontal axis is the orange beam intensity. So at the low intensity of orange beam, the scattering of green beam is constant. So this is linear region. As we expected, the green beam scattering does not, well, it's not affected by the orange beam. However, when we increase the orange beam intensity to high enough, then the scattering of green beam drop significantly. That means we can use orange beam to turn off scattering of green beam. That means green beam does not see the particle anymore, or say the scattering becomes very weak. And we can use this to do all optical switching of scattering with very high contrast, very high modulation depths. It's more than 90% modulation depths. And the switching reversibility is very nice because it's a nanoparticle. So there's also no bleaching. Even though we look at more than 20 minutes, we can actually look at hours without any bleaching. By the way, if you are using fluorescent molecules for this, as we mentioned earlier, the Nobel Prize winning stat using fluorescent molecules to do this on-off gain. And with fluorescent molecules, it's very difficult to sustain the on-off gain for minutes. I mean, not say 10 minutes, even 1 or 2 minutes is difficult. So this really provided very different perspective on this on-off super resolution gain. So following that, we can use this switching on and off scattering to achieve super resolution by adopting a donut beam, just like STED. So the concept is borrowed from STED. So this is a confocal imaging. We only use one green beam to look at several nanoparticles under a confocal microscope. So here, if you make a cross-section here, this looks like a single particle. However, when we add an orange donut into the system, this donut suppresses the scattering surrounding the particle. So if we overlap these two together, the orange donut plus a green laser beam, then we immediately see that there are actually two particles inside this blurred dot. So this is super resolution. This means we can see something previously unseen. And by adding deconvolution, we can make this distinction more clear. So we call this suppression of scattering imaging, abbreviated as sushi, because we collaborated this with a Japanese team. And I hope they are happy about this abbreviation. And this sushi technology has been applied even in cells. So this was published a few years ago by putting these nanoparticles in cells. This is dead cell, not the in vivo cell. So this is ex vivo cells. But we can see nice sushi images of these nanoparticle distributions across the whole cell. So this is the first two parts about plasmonic scattering new contrast. And the third part is the reverse saturated scattering, which we seen previously on, say, silver nanoparticle or gold nanorod. So for gold nanosphere, we also have this linear, then saturation, and then reverse saturation phenomena. So I would like to show here how would the point spread function, which means the focus spot size change versus this intensity variation. So at the low intensity, we have several particles here, and we choose this particle to draw the scattering versus space. So you can see that at the low intensity, there's nothing nonlinear. So the particles show a very nice Gaussian profile because the laser is a Gaussian profile. So the particle, the point spread function show a Gaussian profile here. And when we increase the intensity a little bit, it goes into saturation part, and you can see that the saturation starts from the center as we expected. We mentioned this in sex, right? So the saturation starts from the center, and when we increase a little bit more, the signal actually drops here, which goes into deep saturation, and you can see that every particle becomes donut shape imaging. That means in the center, the excitation intensity is actually higher. However, the scattering intensity is lower. So this is, again, a non-intuitive phenomena, and this non-intuitive phenomena create this strange donut shape due to this deep saturation. And what really is interesting is that when we further increase the excitation intensity, the scattering intensity start to reverse saturate, which means it increase after deep saturation. So in the center, new peaks emerge at this high intensity region, and this creates a shape like the Chinese character mountain. And if we further increase the excitation intensity, it goes to here, which you see this is a very steep part dependency part. So when we further increase the intensity to this deep reverse saturation region, the point spread function actually becomes smaller. The original point spread function is about 200 nanometer, and now the full width half maxima become like 80 nanometer. And the reason is because this slope here is steep. So without any modulation, without any donut beam, we can create a super resolution directly by this reverse saturation of scattering. So this is what I want to show here as the third part of plasmonic based super resolution. So now I'm going to the second main part of a recent result on new super resolution contrast based on silicon nonlinear scattering. So previously we see saturation, we see switchable, we see reverse saturation of scattering in plasmonic nanoparticles. And now we change to silicon nanoparticles and see whether or not we can still see all these interesting nonlinear phenomena. And here I'm going to cover two topics. One is about silicon nanocube. The original purpose of this silicon nanocube is for display. So there are many, many different colors of this nanocube, and you can use this nanocube to form a beautiful painting, nano painting with these nanocubes. And the second part is about anapole enhanced nonlinear response, because anapole has very strong absorption and very small scattering, which should be zero scattering. So by using this anapole, we can have higher heating efficiency while more dramatic slope of scattering variation. So I will start from the first one, silicon nanocube. So the cube we are using is fabricated on quartz, and you can look at this right-hand side imaging by using different size of the cube. The color of the cube is different. So what we have here is actually an array of many different size combinations. So this axis is the size in X, and this is the size in Y. So we have an array of various different size and aspect ratio nanoparticles, silicon nanoparticles. And by analyzing the diagonal line, we see that our experimental scattering intensity fits the simulation very nicely. So from here, we can understand which pole contribute to the scattering of this silicon nanostructure. And here we show several examples to show that this is the first nonlinear scattering of silicon. So for example, if you look at 100 nanometer size nanoparticle, and at a low excitation intensity, everything is linear. But when we increase the excitation intensity, we see very clear saturation of scattering. On the other hand, for 170 nanometer particle, when the excitation intensity is increased, the signal deviates in the positive side, which looks like the superlinear response, and we call this reverse saturation. So for this 170 nanometer particle, you see that the behavior is very different from the 100 nanometer particle, but the same thing is that they strongly deviate from the linear trend of the scattering dependency. And for the 190 nanometer, we see deep saturation behavior of this particle. So all this particle, I mean, we see nonlinear response in many different particles. Here are some examples. So we can see that what we can see in metal nanoparticles, we can mostly reproduce here in silicon. Though the response is not exactly the same, but the main features are actually similar to each other. And the mechanism is also similar to each other. This is due to photothermal effect. And here in silicon nanoparticle, because silicon have distinct Raman scattering peak, so we can use this Raman scattering peak to determine the temperature. So we have better experimental proof that this silicon nanoparticle photothermal nonlinearity is due to laser-induced temperature change, and we can characterize temperature change by the ratio of anti-Stokes to Stokes. And by using this Boltzmann equation, we can determine temperature easily. And with this knowledge, we can actually do simulation. So here you see the simulation result of 3 same particle, 100 nanometer, 170 nanometer, and 190 nanometer. And the color here shows the temperature of the particle. So you can see that we can very nicely reproduce experimental results by simulation. And the inset figure here shows the spectrum shift of individual particle at a different temperature. So the mechanism of this nonlinear response is actually heat-induced spectrum shift, mainly red shift at higher temperature. So that's why this 170 nanometer particle is increasing, because the original location of our laser 561 nanometer is located at a valley of the resonance. So when we increase the excitation intensity, when the temperature of particle increase, the scattering cross-section increase monotonically. That's why we see this somehow interesting superlinear nonlinear response. And everything here is fully reversible, repeatable.
Yeah, very sorry. I have a question regarding the previous slide.
Yes.
So if we take a look at the picture with normalized intensities and Raman scattering, when you compare normalized Stokes and anti-Stokes.
Yes.
So is this the case for some single resonant nanostructure nanoparticle?
Excuse me, single resonance?
I mean, single resonant nanostructure, is this for some cubic structure?
Yes, this is for one specific nanoparticle. Okay. I believe it should be this 100 nanometer.
Okay, so my question is regarding the intensity of Raman scattering when you meet some resonant conditions. So it was shown in 2016 by Pavel Dmitriev and other colleagues of ours that, for instance, magnetic dipole resonance can sufficiently enhance Raman scattering by even 2 orders of magnitude. So I wonder if you're studying a single resonant nanostructure, so how can you compare anti-Stokes and Stokes Raman signals when you're measuring them at different wavelengths? So the spectral distance between the wavelengths at 35 nanometers, it means that at different wavelengths, the same structure can support different resonant modes. So yes, there might be very sufficient differences in intensity. So how can you make sure this this temperature measurement is more or less correct since you're using the intensities. Yeah, thank you.
Yes, yeah, thank you for the question. That's a good point. Indeed, in the model, it should also include a resonance term here. That will make the model more complete. But here, what we want to show is that, well, the temperature can be deduced from the ratio of this anti-Stokes versus Stokes. So I fully agree with you that the model should be revised to consider the resonance change, the resonance, different resonance enhancement of anti-Stokes versus Stokes. However, here what we compare is intensity increasement. So when intensity increase, the ratio, sorry, the ratio changes, and what we want to deduce is the temperature from this ratio changes. So even if there is resonance enhanced, say for example, this anti-Stokes, maybe this anti-Stokes has higher, if I look at the spectrum, okay, if I look at the spectrum here, maybe this Stokes peak has higher resonance enhancement compared to its anti-Stokes peak, am I right? Because here you can see the spectrum of 100 nanometer, the right-hand side has larger resonance than the left-hand side. So this Stokes peak may have larger resonance enhancement. So what I agree with you is that we should add one more term here to compensate this enhancement. But qualitatively, this change of ratio due to increase of excitation intensity still reflect the temperature enhanced dramatically. And because the ratio here is not a small value, you can see that the ratio changed from 0.2 to 0.4 to 0.6. So the ratio changes significantly at different excitation intensity, and this reflects the temperature actually changed to like 900 degrees C. So this is a significant heating of nanoparticle. Do I answer your question?
Yeah, thank you very much. So if you mentioned the significant heating in nanoparticles, there's an approach, maybe it was even predicted by Balkansky in PRB in 1983, that for crystalline silicon or germanium, one can use just only Stokes signal and its spectral shift to distinguish the temperature directly. So you can avoid this. You can avoid this comparison between anti-Stokes and Stokes intensity just by using a very, I would say, great resolution in Raman scattering. So yeah, it requires maybe a more expensive setup, but it works fine. So thank you. Yeah,
yes, yes, fully agree. Yeah, I think George yourself is an expert on measuring temperature.
not pretty much an expert, but I'm trying to be an expert. Yeah, thank you. Yeah, so I think there's another question by Dr. Mikhail Petrov. Yeah, Misha.
Yeah, but I just wanted to add to this discussion that it would be super interesting to see these Stokes, anti-Stokes temperature and the temperature derived from this shift, from the shift of the resonance. Yeah, how, because you have it for different now sizes, right? So as if I understand it right, yeah? So then it really brings, it might bring a big difference. So I fully agree that it's qualitatively it will be the same, but then the numbers, so then you kind of measure this Purcell ratio at Stokes and anti-Stokes. So that would be super interesting to have a look at. Yeah.
Yeah, thank you. So we do have one student who is working on this better characterization, because this is just to demonstrate we do see this temperature change, but we do have one student working on more detailed temperature characterization of different size of nanoparticle during this laser-induced heating.
Right.
So I will bring your suggestion to him that it will be worthwhile to work on this shift-based thermometry. Yeah, thank you very much.
Yeah, we have some theory on that, so I think we will be glad to share some papers with you, right? Okay, thank you.
Okay, yeah, that's wonderful.
It's fascinating result, right?
Thank you very much. Yeah, I'm more than happy to collaborate. I mean, this is the purpose of giving a seminar, right? So in case you have any idea, please feel free to contact me. I'm more than happy to work together.
Yeah,
so next one is we want to show the reversible and repeatable nonlinear response. So yeah, I think this is straightforward. The point-spread function changes and come back, change and come back. So we can simply use point-spread function I think this is a convenience of using imaging because we can see the nonlinear response. Yeah, we don't need to measure power dependency. We can see nonlinear response.
Я знал, есть правосудие.
Excuse me?
I'm very sorry. I think this was like a misuse. Sorry.
Okay, yeah, that's fine. So yeah, so this is just to show visually, we can see reversible and repeatable nonlinear response. And here we quantitatively derive the nonlinear response, again, using N2. So the N2 approach 0.1 micrometer square per milliwatt. So it's about 1 order smaller than gold, but compared to bulk silicon, this is 5 orders larger than photothermal response of bulk silicon. And we can achieve like 0.2 change of index by photothermal response. So sorry, I don't go into details here. Yeah, it's almost 4 now, so I don't want to spend too much time of you. So once again, my main interest is in imaging. So now we see saturation of scattering. So certainly we can use SAX again to enhance spatial resolution. So this is a result of enhancing point spread function. And very interestingly, we see strange images when we look at the silicon nanoparticles. To be honest, I have no idea what's this. And so this is 1F, 2F, 3F image. And so you see the point function shrinks, but the shape of the image is very different. And we are looking at a single nanocube. So I have no idea why we see this, say, circular shape of images. So if you are interested in this, maybe this is another possibility of a collaboration to explain what we see in experiments. And in addition to this nonlinear response, certainly we mentioned that when we see saturation, we can do all-optical switching. So we also demonstrate this all-optical switch in silicon. So once again, we achieve this 90% modulation. And we also use pump probe to measure the relaxation time. So the relaxation time is about 1 to 2 nanoseconds. That means we can use this nano silicon to do gigahertz modulation with modulation depths above 90%. And certainly we can also do this, we can also use this all-optical switching to achieve super resolution, but this is ongoing, so I don't have a result now, but you can imagine this is certainly doable. So the last part I would like to cover is that we can further enhance the nonlinear response in this silicon nanoparticle via anapole. And this is collaborated with Professor Xiangping Li and Dr. Tianyou Zhang in Jinan University of China. So we just published this in Nature Communication recently. So here we use nanodisk, which is well known to have anapole response when the size is correct. So in the simulation, you see that this is wavelength, this is the size of silicon nanodisk. So there's an anapole line here. So what we use here is the size of nanodisk is 170 nanometer, and we use 532 as the excitation wavelength. So at the low intensity, the main scattering comes from electric dipole, which is this peak. And when we increase excitation intensity, this sample is heated up and the whole spectrum redshift. So I move the spectrum shift to the right. So you can see that when the spectrum shift to the right, this wavelength 532 go across anapole and then increase again. So we can imagine that when we look at the power dependency, we should see linear at the low intensity, then the scattering drops dramatically due to anapole. This is a saturation. And then the scattering come back again due to another electric dipole on the left-hand side of anapole. So this is reverse saturable scattering. So we can observe this saturation and the reverse saturation in this nanodisk. And this is very high suppression due to anapole. So if we look at the point spread function at the focus at the linear region, the whole point spread function is a Gaussian. And then at the saturation, it becomes donut. We have seen this before. At the reverse saturation, there's a small peak coming out in the center. So the idea of super resolution here is that we can use reverse saturation plus subtraction directly. So we don't need SAX, we just subtract this reverse saturation to this saturation image, and by subtracting these two, we get a very small peak in the center. So this can help us to localize the center of the silicon nanostructure. So if you look at an array of silicon nanodisk, so at the low intensity, you basically see nothing because this is too dense. And when we increase excitation intensity to saturation and to reverse saturation, you see that we can see individual particle, and in the center, there's a small peak coming out. So when we subtract these two, when we subtract reverse saturation to saturation, then we get a very small peak in the center, and the localization precision can be down to 50 to 40 nanometers. So this is the third way that we can achieve super resolution in silicon. And we can identify the location of each silicon nanodisk very nicely. So in summary, we have seen nonlinear scattering in metal and silicon nanostructures. What we see is saturation of scattering, switchable scattering, and also reverse saturated scattering. And consider the nonlinearity N2, we have 3 to 5 order enhancement over bulk. And this is due to photothermal effect plus Mie-resonance, and this can be further enhanced by anapole in silicon nanostructure. So in terms of optical microscopy, we can achieve super resolution by various methodologies. So for example, we demonstrated in metal, in silicon, by saturation scattering plus SAX, we can achieve like 65 nanometer resolution. And in metal nanoparticle, we achieve switchable scattering plus sushi. We can do like 80 nanometer spatial resolution. And for reverse saturated scattering in gold and in silicon, we can also achieve very nice super resolution, especially in silicon. We have 40 to 50 nanometer localization precision. And the best of all is that there's no bleaching at all for this optical scattering. And so this is a new method for super resolution in material because we don't need to label anything. So in the future, we are going to continue to explore this nonlinear nanophotonics part, and we seek to further increase this already giant nonlinearity to be even larger. And we hope to apply this to deep tissue super resolution because this is a very challenging field in terms of super resolution. And since I mentioned we can do all optical switching, so there's also a possibility that we can apply this nanostructure, no matter it's gold or silicon, especially silicon would be more interested in constructing these all optical circuits. So I would like to thank our collaborators. For many of the work I played together with my colleagues in Osaka University, including Professor Kawata, Professor Kazumasa Fujita. For silicon, I especially thank Professor Junichi Takahara, also in Osaka University. And yeah, Yonatan's here. I really like to thank Yonatan to provide strong support when simulating this plasmonic nanoparticle scattering. And for silicon anapole part, I worked together with Shangping Li and Tianyou Zhang in Jilin University. And for PUNCPRO, it was done by Dr. Gongxuan Lin in Academia Sinica. And for thermal measurement, Dr. Zhiwei Zhang in NTU in my university helps a lot. So these are my acknowledgements. And more importantly, though I'm the one who gives talk here, these are the person who really did all the measurements. So these are my students. Deika is my postdoc. He's now in India as an assistant professor. Hou Xian did all the early silicon nanoparticle thing, and Alan initiated this silicon thing. And Dexing, Yulong, and Bang Han are current students, and they are continuing this plasmonic and silicon nanophotonics exploration. So this is our campus, this is my university, and this is a famous Taipei 101. I hope in the future you will have the opportunity to visit our hometown. Thank you very much.
Thank you very much, Professor Shi Wei Chu. So first of all, thank you very much for giving your talk and accepting our invitation. And then my suggestion is we have a quick discussion. We have still some time for discussion. So yeah, please, Misha, I see your hand.
My hand? No, I actually didn't.
Okay.
I just wanted to thank once again for very nice talk. And I had a pleasure to visit Taipei once, so it's really a nice.
Okay, you're welcome to visit again.
Thank you. As soon as it will be possible.
Yeah. Now it's difficult, but yeah, things will be better, I hope.
Okay. Thank you.
So yeah, Professor Shi Wei Chu. So there are a few questions in the chat, so I can read them. First one is from Dr. Sergey Makarov. So maybe during the talk you already mentioned, so even from my side, so did you observe any spectral shift of both like anti-Stokes and Stokes Raman signal upon like higher intensity laser radiation?
Sorry, I don't see the question. So should I?
No, it's just it's just a question from my side, which is combined with some question from which is partly combined.
Sorry.
So when you observe this anti-Stokes and Stokes Raman scattering, have you observed some slight, probably spectral shift of those signals?
Of course.
Okay. Okay, that's great. So this is the brief question from my side. Yeah.
As you are suggesting, we can actually use this spectral shift to determine the temperature.
Okay, that's great. Yeah.
Yep.
So I will keep on. So Dr. Sergey Makarov is wondering, did the authors observe any irreversible reshaping of silicon nanoparticles? So he's mentioning some paper which I'm scared to open since I'm the host of the seminar. So yeah, can you please comment? Were there any irreversible?
That's a good point. So certainly, whenever we are playing with nonlinear response, we get into competition with damage. So it really depends on which come out first. So let me show you one figure that I did not show earlier. So this is the array I mentioned that we have. So you can see my slide, right?
Yes.
Okay, good. So this is an array of our nanoparticles. So we have many different sizes of nanoparticle, and this is the nonlinear response in this array. So you can see that even though we have many particles that do have nonlinear response, this blue means negative nonlinearity, like saturation, and this red means superlinear, like this 170 nanometer particle. So, but you can also see that there is a region that we don't really see nonlinear response, and the reason is because when we pump the particle too much, it damaged. So nonlinearity does not always show before damage. And I think the reason mainly is because where is the resonance of the particle compared to my excitation wavelengths. The figure you see here is made by 561 nanometer laser. So I believe if I change to another excitation wavelength, I can see nonlinear response here. It's just now this region is not sensitive to 561. So I didn't see nonlinear response here. So if I pump too hard, the particle really damages. So even if those who show nanoparticle, even if I show reversible response, if I pump, so currently I think I use 6-7 milliwatt per micrometer square. If we go up like, if I remember correctly, it's like 20 or 30. So if we go up like 20 or 30 milliwatt per micrometer square, everything damaged. Okay, so I hope this answers your question. So indeed, particle damage.
Yes, I think pretty much. So yeah, thank you very much. So there's another question by Marco Gandolfi from Brescia, as far as I remember. So he wonders, first of all, he thanks you for the very nice talk. So, and he wonders, so you mentioned nonlinearity. So how does these results map into like nonlinear susceptibility tensors like chi2, chi3, etc.?
Okay, yeah, that's a good point. Sorry, I didn't go into detail here. Yeah, I believe maybe Yonatan can give a better explanation, but let me try to explain briefly. So I use the equation of N2 to describe a nonlinear response. And in the literature, sometimes you see people exchange N2 with chi3 retrospectively. However, this N2 and the chi3 exchange is only valid when the nonlinearity is ultra fast, which means instantaneous. For example, the current nonlinearity. So if it is not instantaneous, then we should use N2 to express the nonlinear response, like hot electron, like hot lattice induced nonlinear response. The reason is because if you think about the equation of chi2, chi3, it is linked with electric field. So that means the chi2, chi3 nonlinear response is due to field strength induced nonlinear response. So that is typically instantaneous. And what we're doing here is intensity induced nonlinearity, like temperature. It is induced by excitation intensity. That's why I use N2. And here, my N2 definition cannot be exchanged into chi3 because this is not instantaneous, not field induced nonlinearity. Do I make myself clear?
Yeah, at least for me, yeah, thank you very much. So
would I be able to add something to this?
Yes, sure, please, yeah.
Yeah, so Shi Wei's answer was very good. If I can add from my own perspective, then basically all these chi2, chi3, etc. expansions rely on an electronic response, which is instantaneous. Whereas, and local in time and space. However, I think Shi Wei, everything you showed is thermal effects, and
Yes.
these are non-local in space and in time. And for those mechanisms, the chi2, chi3 standard descriptions are just not suitable. So it's just, I mean, people use them all the time because they are used to do that, but fundamentally, this is, in my opinion, not correct.
Yep. Thank you.
Yep, once again, so maybe last question from my side. So do I understand correctly that N2 is also strongly dependable on the wavelength? So for every single wavelength you were considering, you were using different N2s?
Yes, I mean, now, because now, especially now, what we have is due to the Mie-resonance. So certainly this N2 all are wavelength dependent. So for example, in one of the slides, I didn't talk into detail. So the figure D here actually shows that the N2 value changes. So this must happen when we are talking about this Mie-resonance induced nonlinearity.
Okay.
Yes.
Okay. With that, I think, yeah, thank you, Yonatan, for the link. Yeah, please use this link to study thermal effects for chi3. So with that, I would like to thank Professor Shi Wei Chu once again for accepting our invitation, giving a very, very brilliant talk, exciting results, impressive papers. So with that, I would like to close the seminar, and thanks everyone for joining us. Thank you. Yeah.
Sorry, suddenly I disappeared.
Yeah, maybe it was something wrong with my connection.
That's okay, but thank you very much.
Yeah, thank you once again.
Thank you.
Yeah, take care.
Yeah, bye-bye.
Thank you much. Bye-bye.